Hi, welcome back to Unit 4, Day 2. This is Part 3, where we're going to look at ionic bonds now. Remember that for this first half of the video, you'll be taking sections in note section B of your Week 1 notes. So before I sort of go into the lesson, I want to sort of recap where you should be at in your Week 1 note packet. So we've already covered Part A, which was covered in video Part 1. What you want to do is have answered those questions already, and that goes for everyone, both honors and fundamentals of chemistry. In the last video, we learned about metallic bonding. So for Part B, you should have the information filled out for the first column of that table. So the types of atoms, give examples, the name of the bond, and the properties. And then finally, for Part C, this is required for honors chemistry, but optional for fundamentals of chemistry. You should have filled in this table for the metallic bond section. Okay, so let's go right in now into ionic compounds. And here are some examples of ionic compounds. You can see they have a lot of different colors and they're all solids. So in this section, what we're going to do is we're going to learn what type of atoms that they're made of, describe their bonding, learn about their properties, and explain their properties using bonds. Okay, so ionic bonds and compounds. Well, what are they made of? Ionic bonds are made of metals and at least one nonmetal atom. So if you look on the periodic table, and if you're looking at your chemical formula, and you see you have a metal, an atom that's classified as a metal, and an atom that's classified as a nonmetal, you know that you have an ionic compound. Now, substances that have ionic bonds are called ionic compounds, and they're also known as salts. And examples of that would be NaCl, known as sodium chloride, which is also known as table salt. So table salt is an example of an ionic compound. Magnesium sulfate, MgSO4. So you have a metal, magnesium, and then S and oxygen. Those are both nonmetals. So that's an example of an ionic compound. This is also known as Epsom salt. So the thing that people put in their bath to sort of help relax them. And the last example here, we have calcium fluoride. So again, we have a metal, calcium, and then a nonmetal, fluorine. Okay, so let's take a moment to pause and see where we're at here. Which of the following is an ionic compound? And you have a list of chemical formulas here. And to sort of help you out with that, I have highlighted where all of these elements are on the periodic table, so you don't have to look too hard to find them. And we also have this color-coded periodic table. It makes it easy to know if something is a metal, metalloid, or non-metal. All right, so what you're going to do is you're going to pause the video and using the definition that we saw on the previous page, that ionic bonds are made up of metals and non-metals, identify which one is an ionic compound. When you press play again, the answer will be revealed. Great, so the answer is C. If you look at choice C, we have lithium, which is a metal, and fluorine, which is a non-metal. So we have a metal and a non-metal, makes it an ionic compound. All right, so now let's go into how ionic bonds are formed. And this is going to be super helpful later when we learn about Lewis dot structures. Okay, so the first step is that the metal in the ionic compound loses or gives its valence electron away to a nonmetal. So we have sodium Na, which is a metal, and it's going to give its outer or valence electron to fluorine, the nonmetal. Now, when it does that, the metal, since it's lost an electron, becomes a cation. It becomes positively charged. And the nonmetal, fluorine, since it gained an electron, becomes an anion, or negatively charged. Now, because opposites attract, according to laws of physics, the positive and negative, the positive cation and the negative anion, they're going to want to hang out, right? Sort of like how two magnets of opposite poles come together. That's what's happening here. And that's actually what forms the ionic bond, that opposite attraction of the metal cation and the nonmetal anion. Now, when you have a bunch of these metal cations and anions, you form a lattice. So ionic compounds sort of look more like this. They don't just look like two separate, two atoms connected together. They're sort of in a lattice or network as shown here. So you have the negative anion and then the metallic cation. One quick note, because the metals lose an electron, they actually become smaller when they form a cation. And the nonmetals become slightly bigger. So a lot of times in the lattice diagrams, you'll see the cations shown as a smaller circle and the anions shown as larger circles. Okay, so this is sort of just an animation just to visualize what's happening here when ionic bonds are formed. Key thing being that when an ionic bond is formed, the metal loses an electron, becomes a cation, and the nonmetal gains an electron, becomes an anion. All right, so this sort of leads us back to the common charges that we learned about before. Remember we learned about common charges? Those are the charges that an atom would likely have in an ionic compound. So it comes from this idea of metals losing electrons and nonmetals gaining electrons. Remember, they're doing that to sort of have an octet, to have that satisfied shell. All right, now that we looked at how ionic bonds are formed, what they look like, let's talk about some properties of ionic compounds. So you want to make sure in your table that you're listing down these properties as we go through them. Starting with their phases. Ionic compounds are solids. They're all solids. As you can see here, they do have various colors, so they can have different colors. They're dull, they're not shiny. And in terms of conductivities, they're insulators when they're a solid. However, they're good conductors if they're molten, which means they've been melted, or if they're aqueous, which means they're dissolved in water. So let's pause here for a moment to sort of visualize that. So this is super important. Ionic compounds do not conduct as a solid. So if you have a solid chunk of salt, which is shown here, and you put a conductivity meter on it, it's not lit. It's not going to light up. It's not going to conduct electricity. However, if you took that salt, that chunk of salt, and dissolved it in water, or you melted it down, and then you put the conductivity meter in that sample, it will be lit. It will conduct electricity. So the key thing, ionic compounds do not conduct as a solid. They're insulators as solids, but they do conduct when dissolved in water or molten. All right, last few properties. They are brittle, so if you hit them, they're going to break. Many of them are soluble in water. Not all will dissolve or be soluble in water. They have high melting points and high boiling points, and they're hard. So now we're going to move on to using the bonds to explain those properties. For honors chemistry, remember you're required to take these notes, and for fundamental chemistry, this is optional. All right, so let's begin with their solubility. Why are many ionic compounds soluble? What happens with an ionic compound when you put it in water? The lattice, which connects the positive cations and the negative anions together, will break apart in the water. And because water is a polar molecule, which we'll learn more about later, the water molecule itself has a positive and negative side. The negative side is where the very electronegative oxygen is. So that's slightly negative. And the positive side is where the less electronegative hydrogen is. And so what happens, as you can see in this picture, the water molecule is able to surround the ions. Now, ions don't like to be free off by themselves. So in order for the lattice to break apart, the water molecules have to sort of surround it in such a way to stabilize it. And that's the reason why many ionic compounds can dissolve in water, because water will stabilize it by surrounding it in a certain way. Now, if the lattice energy, or the energy holding that lattice together is very high, then they will not dissolve. So that's why some salts don't dissolve, just because they have a high lattice energy. If you want to see more of this animation in terms of a salt being dissolved in water, you can click on this link. All right. Next property we're going to talk about is conductivity. So as we said, ionic compounds are insulators as a solid. And the reason why that they're insulators as a solid is in order for a substance to be a conductor, they have to have mobile charges, so like electrons or whatever, or cations or anions. And when the ionic compound is a solid, in the lattice, those cations and anions are not moving anywhere. They're fixed in place. So they're not going to conduct as a solid because cations and anions cannot move when it's a solid. However, if you dissolve it in water, if you melt it down, those ions sort of break apart and they're able to flow and to move. And so as a result, when you melt an ionic compound, so when it's molten or when it's dissolved in water, aqueous, it will conduct. All right. The fact that ionic compounds are brittle has to do with when you hit an ionic compound, you sort of destroy that lattice. So one key thing that keeps the lattice together is that you have alternating positive and negative charges next to each other. But if you hit it, what could potentially happen is the two like charges, so two negative charges, will get together and then that will cause them to repel, thus breaking that bond. So the reason why they're brittle is when you hit them, you destroy the lattice where there's alternating positive and negative charges. Now, the last property we're going to talk about is high melting point and hardness. So ionic compounds, just like metallic bonds, are arranged in a network. And remember, networks strengthen those bonds because you're not just breaking apart one thing, you have to break apart a lot of things. So because they have ionic compounds are arranged in, or ionic bonds are arranged in a lattice or a network, they're going to have high melting points and high boiling points because it takes a lot of energy to sort of separate those atoms. And that's also the reason why many of them are hard. And we can take a look at their melting points. So if you look at them, like again, they're like the high 100s and into the thousands. So ionic compounds can have really, really high melting points. All right, so that's it for this video. The next video, we're going to talk about molecular covalence.